Dear students, so today let us we study about the topic the solids. So as you know, there are four states of matter: the solid, liquid, gas and the plasma. You have studied in the earlier classes. In solids, atoms are very close to each other. In case of liquids, they are slightly away from each other. In case of the gases, they are still away from each other. And in case of a plasma, it is a state of ionic. Among these four states of matter, so let us we study in detail about the topic, the solids. Solid is a state of matter characterized by definite shape and volume. In solids, component particles are compactly arranged and held together by strong interparticle force of attraction. Solids are rigid and non-compressible. Solids have good mechanical strength due to close packing arrangement. There are two types of solids: crystalline solids and amorphous solids. The crystalline solids are those in which particles are regularly arranged in a definite geometrical pattern, whereas in amorphous solids, particles are not arranged in geometrical pattern. Crystalline solids have sharp melting point, whereas amorphous solids, they do not have sharp melting point. However, they melt over a range of temperature. Crystalline solids are anisotropic. It means physical properties measured in different directions are different, whereas amorphous solids are isotropic. It means physical properties measured in different directions are same. Crystalline solids are the true solids. Example: sodium chloride, diamond, gold, etc. Amorphous solids are not true solids. Example: glass, rubber, plastics, etc. Here I have shown how the atoms, molecules or ions, they are arranged in crystalline and amorphous solids. In crystalline solids, they are perfectly arranged, whereas in amorphous solid, these are haphazardly arranged. Atoms, molecules or ions are shown in the form of a sphere. I have given an example of marble, which is a crystalline solid, is having a definite geometry, whereas a chalk, it is an amorphous solid where the atoms are haphazardly arranged. Another example, the quartz. Quartz is nothing but it is a silica where it is a crystalline solid. The atoms are perfectly arranged. In case of a glass, which is an amorphous silica where atoms are haphazardly arranged. Below I have shown the types of crystalline solids. The crystalline solids are of four types: ionic crystals, covalent crystals, molecular crystals and metallic crystals. Coming to the ionic crystals, they have oppositely charged ions arranged alternatively. The binding force is the electrostatic force of attraction. Since the ions are not mobile, hence do not conduct electricity. They are soluble in water and the solution conducts electricity. Ionic crystals are hard and have high melting point. The examples are sodium chloride, potassium chloride, cesium chloride, calcium fluoride, potassium nitrate, and so on. Covalent crystals. Atoms of these crystals are held together by covalent bond. They do not conduct electricity in the solid state or even in solution. They are soluble in non-polar solvents. They are hard and have high melting point. Example, diamond, silicon carbide, etc. Coming to the third type of the crystals known as molecular crystals. Molecular crystals are composed of molecules. They are held together by weak van der Waals force of attraction or dipole interaction or hydrogen bonds. They are moderately hard and have moderate melting point. They are bad conductors of electricity. Examples, solid iodine, dry ice. Dry ice is nothing but it is solid carbon dioxide, etc. Coming to the fourth type known as metallic crystals. Metallic crystals have cations of the metal atoms surrounded by mobile electrons. Electrostatic force of attraction is in between cations and electrons. This is called a metallic bond. Metallic crystals are good conductors of heat and electricity, and they are hard and have high melting point. All metals like gold, silver, sodium, iron, etc. they come under the class metallic crystals. Now coming to the crystal systems. Now if I take any crystals, all these crystals, they are characterized by their crystal lattice, their coordination number and unit cell. Now let us know what is this crystal lattice. Crystal lattice is a pattern which indicates the regular arrangement of component particles like atoms, ions or molecules in a three-dimensional space of a crystalline solid. It is also called a space lattice. So the points indicate the position of component particles like atoms, ions, molecules in the crystal. It is called lattice points. The vacant space is called interstitial space or void volume. Here I have shown a crystal lattice of potassium chloride. Coming to the another unit cell. A unit cell is the smallest unit of the crystal lattice which describes all the properties of the crystal. The entire crystal consists of a large number of unit cells adjacent to one another in all the three dimensions. It may be noted that the properties of crystalline solids depend not only on their composition and external conditions but also on their internal structure. For example, although diamond and graphite are composed of the same substance, that is carbon, they have different properties. The difference in their properties is due to the difference in their internal structure. Coming to the crystal systems. The shape of a given crystal can be described by the length of the three sides or edges given as A, B and C of its unit cell and the three angles alpha, beta and gamma between the three axes of the unit cell. The length of the sides of the unit cell are called primitives or crystal axes, and the angles between the three axes are called interfacial angles. Here I have shown a crystal lattice or a space lattice. So the space lattice contains the large number of the repeating units, and that repeating unit is also shown here, that is called unit cell. This unit cell is having the crystal axes below I have shown A, B and C, and also interfacial angles alpha, beta and gamma. Now there are 7 different unit cells. These 7 different unit cells are named as the cubic, tetragonal, orthorhombic, hexagonal, triclinic, monoclinic and rhombohedral. These 7 crystal systems, they differ in the crystal axis and also interfacial angles. Here I have shown the various crystal axes A, B and C and also the interfacial angles in all these 7 crystal systems. There are 7 crystal systems corresponding to the 7 distinct types of unit cells. They are cubic. In this case, A is equal to B is equal to C and alpha, beta, gamma all are 90 degree. Example of this type are sodium chloride, potassium chloride, calcium fluoride, alums, diamond, etc. Second one is monoclinic. Here A is not equal to B, which is not equal to C, and alpha and beta interfacial angles are 90 degree and gamma is not 90 degree. Example, sodium sulfate decahydrate, sodium bicarbonate, ferrous sulfate heptahydrate, monoclinic sulfur. The third one is triclinic. Here A is not equal to B, which is not equal to C, and all the angles are also not equal to 90 degree. The example, cuprous sulfate pentahydrate, potassium dichromate and boric acid. The fourth category of the crystal system is the tetragonal. Here A is equal to B, but B is not equal to C. Alpha is equal to beta, but beta is not equal to gamma, but however they are 90 degree. Example, nickel sulfate, white tin, stannous chloride, titanium dioxide, etc. are the examples of this category. The fifth type is orthorhombic. In this case, A is equal to B, but B is not equal to C. Alpha is equal to beta is equal to gamma is equal to 90 degree. Potassium nitrate, barium sulfate, magnesium sulfate heptahydrate, rhombic sulfur are the examples of this category of the unit cells. The sixth one is rhombohedral or trigonal. In this case, A is equal to B, B is equal to C, and alpha is equal to beta, beta is equal to gamma, which are not 90 degree. Example, calcium sulfate, sodium nitrate, potassium permanganate belongs to this category. The last one is hexagonal, where A is equal to B, but B is not equal to C. alpha is equal to beta is equal to 90 degree, whereas gamma is equal to 120 degree. The graphite, silica, silver iodide, ice, lead iodide, zinc oxide are the examples of hexagonal crystals. Coming to the Bravais lattices. In 1848, Bravais showed that there are 14 space lattices in the 7 crystal systems mentioned above. These are called Bravais lattices. Here I have shown whatever I have explained in the form of a diagram. So in the cubic system, we have 3 types. One is known as primitive cubic, another one is body centered cubic, and third one is phase centered cubic. In tetragonal, we have 2 types, primitive or simple tetragonal, and second one body centered tetragonal. The third one, orthorhombic. In this structure, we have primitive orthorhombic, body centered orthorhombic, phase centered orthorhombic unit cell, and lastly the side centered orthorhombic crystal. In hexagonal, we have only the primitive type. In trigonal also we have only one primitive type, and in triclinic also we have only one primitive type, or the simple unit cells. In monoclinic, we have primitive unit cell as well as side centered unit cell. If you totally add all these unit cells, it becomes 14, and all these 14 unit cells are called Bravais lattices. So here I have shown the same explanation. Now coming to the structure of metallic crystals. Most of the metals belongs to S and D block elements in the periodic table. And these metallic crystals have any one of the following structure. The metallic crystals may be having hexagonal close packed structure known as HCP. They may have cubic close packed or phase centered cubic structure called FCC, and third one, body centered cubic structure known as BCC. Now these 3 have the following characteristics. In hexagonal close packed and cubic close packed, the packing of atoms is very close to each other, whereas in BCC they are not that much close packed. In hexagonal and cubic close packed structure, volume occupied by the atoms is 74%, whereas in case of body centered it is 68%. The atoms in each the packing in each the level, it is having AB type of packing, whereas in cubic close packed it is having ABC type of the packing. However, this you don't find in body centered cubic lattice. The coordination number, which you will be studying later on. So in hexagonal close packed it is 12, in cubic close packed also 12, in body centered cubic it is 8. Hexagonal close packed metal crystals have less malleable and ductile. Cubic close packed metal crystals are more malleable and ductile, and the body centered cubic lattice crystals are normal, malleable and ductile. The examples of the metals having hexagonal close packed structure are chromium, molybdenum, vanadium, magnesium, zinc, etc. The metals having cubic close packed structure are copper, silver, gold, nickel, platinum, etc. And the metals having the body centered cubic lattice, they are all alkali metals. Here I have shown the hexagonal close packed structure. So here the first layer, the atom is surrounded by the 6 other atoms in one plane, and above the plane 3 atoms are arranged, and below the plane remaining 3 atoms are arranged. And in hexagonal close packed structure, the above and below planes, they have arrangement of atoms is the same, which I have shown in a blue colored the diagram. So this is known as hexagonal close packed structure. Here it shows the central atom in one plane, it is connected to 12 other atoms, 6 in one plane and 3 are in above and below the planes, hence the coordination number becomes 12. In case of cubic close packed arrangement, so the first and the third layer, they are different, their arrangements are different, even though the 3 atoms are there, so they are different. So hence this type of arrangement is known as ABC type of the arrangement. I've explained this even with the above diagram. The same thing in a ray diagram form we can show like this. Hexagonal close packed structures have this type of the arrangement. The cubic close packed and body centered cubic lattices have these structures. Now coming to the interstitial sites in close packed arrangement. As I have said, between the atoms we have some space. This space is called interstitial space, or it is also called void volume. Now let us study how much space is there between the atoms in a different crystals. So the interstitial sites formed in between closely packed atoms of a given crystal are, they have triangular or trigonal site. The next we have tetrahedral site, and third one octahedral site. Coming to the trigonal site, the empty space left between the 3 touching spheres is called trigonal site. The radius of the atom fitting into this space should not be greater than 0.155 times that of the surrounding close packed spheres. In case of tetrahedral site, the empty space left between the 4 touching spheres in tetrahedral geometry is called tetrahedral site. The space is greater than triangular site. Hence the radius of the atom fitting into this space should not be greater than 0.225 times that of the surrounding close packed spheres. The octahedral site is generated by 2 equilateral triangles whose apex point in opposite directions. There is only one octahedral site for each sphere. It should be noted that the number of octahedral sites is half the number of tetrahedral sites. Hence the radius of the atom fitting into this space should not be greater than 0.414 times that of the spheres forming octahedral site. Let us take here, I have shown a diagram showing the tetrahedral site, the triangular site and the octahedral site, where the, the space in it. And this diagram shows the stability. So if in the wide volume, if the cation size is smaller than the size of the anion, then if it is fits in this condition, such ionic compounds, they are not that much stable. So in the second case, of course, they are moderately stable. It's not that much stable because they fit it into the wide volume. But in the third case, so the size of the cation is the bigger. So therefore, this type of the ionic solid is much more stable. Now, let us take the another aspect, that is the coordination number. The number of particles which are directly in contact with a given particle in the three-dimensional space is called coordination number. It gives the total number of particles immediately adjacent to each particle in the crystal lattice. In other words, coordination number is the number of nearest neighboring particles. It depends on the relative size of particle and the type of close packing arrangement. In simple cubic lattice, each atom has 6 nearest neighboring atoms. Hence, coordination number is 6 in simple cubic lattice. In body-centered cubic lattice, each atom has 8 nearest neighboring atoms. Hence, coordination number is 8. In hexagonal close-packed structure and in cubic close-packed structure, each atom is in contact with 6 other atoms in one plane and 3 other atoms in above and below the planes. Hence, the coordination number is 12. Now, let us take some other examples wherein the coordination numbers in case of ionic crystals. Ionic crystals of the type AB, let us take first. Sodium chloride is an example of AB type of an ionic crystal where the number of ions in both the cases is 1:1. This type of ionic crystal is having 6:6 coordination crystal or coordination number. Here, each sodium ion is surrounded by 6 chloride ions and each chloride ion is surrounded by 6 sodium ions. Hence, coordination number of sodium is 6 and chloride is also 6. Other examples of this category are sodium iodide, potassium chloride, rubidium iodide. Now let us take another ionic crystal, that is cesium chloride. Cesium chloride is having 8:8 coordination crystal. Here each cesium ion is surrounded by 8 chloride ions and each chloride ion is surrounded by 8 cesium ions. Hence, coordination number of cesium ion is 8 and chloride ion is also 8. The other examples of this type are cesium bromide, calcium iodide, tantalum chloride, tantalum bromide, tantalum iodide. The third category is known as zinc blende crystal. Zinc blende is nothing but it is zinc sulfide crystal where both have 4:4 coordination. Here each zinc plus 2 ion is tetrahedrally surrounded by 4 sulfide ions and each sulfide ion is tetrahedrally surrounded by 4 zinc ions. The other examples of this type of the zinc blende crystal are cuprous chloride, cuprous bromide, cuprous iodide, silver iodide, beryllium sulfide. In zinc blende crystal, sulfide ions are in a cubic close packed structure. We also have the same zinc blende, another structure called Wurtzite crystal. This is also a zinc sulfide crystal where both have the coordination number 4. But the difference is here, in Wurtzite structure, sulfide ions are in hexagonal close packed arrangement. In case of zinc blende, it is having cubic close packed arrangement. In case of Wurtzite, it is having hexagonal close packed arrangement where rest is the same. Coming to the another type of ionic crystals, that is Ab2 type. The example is fluorite crystals. Example, calcium fluoride. Here, each calcium ion is surrounded by 8 fluoride ions which are placed at the corners of the cube, and each fluoride ion is surrounded by 4 calcium ions which are placed at the vertices of tetrahedron. So therefore, the coordination number of calcium is 4 and coordination number of calcium is 8 and coordination number of fluoride ion is 4. Other examples are strontium fluoride, barium fluoride, strontium chloride, barium chloride, cadmium fluoride, mercuric fluoride. We also have another structure called rutile crystals. The rutile crystals are nothing but it is titanium dioxide, where it is to have 6:3 coordination crystals. Here, each titanium ion is octahedrally surrounded by 6 oxide ions, and each oxide ion is surrounded by 3 titanium ions placed at the corners of a triangle. Other examples of this category are nickel fluoride, cobalt fluoride, manganese fluoride, magnesium fluoride, zinc fluoride, stannic oxide, lead dioxide, manganese dioxide, and so on. Here I have shown the different crystals and their coordination numbers. In body-centered crystal lattice, the coordination number of cesium is 8. So where the red colored cesium ion is surrounded by 8 chloride ions, and similarly each chloride ion is surrounded by 8 cesium ions. Now coming to how to calculate the number of particles in each unit cell. In simple cubic lattice, in a cube there are 8 atoms, and this cube is surrounded by 4 other cubes in one plane and 4 other cubes above the plane. Therefore, each atom is in contact with 8 cubes. Therefore, the 8 atoms are there in a cube, and the contribution of the atom in each cube is 1/8. Therefore, 8 into 1/8 is equal to 1. So, in simple cubic lattice, the number of particles in an unit cell is 1. In case of body-centered cubic lattice, so we have, because 8 atoms are at the 8 corners, therefore 8 into 1/8 becomes 1. And at the center of the cube, we have 1 atom. So therefore it is 1 plus 1 is equal to 2. In case of body centered cubic lattice, we have 2 atoms in an unit cell. Coming to the phase centered cubic lattice. In case of phase centered cubic lattice, as usual, 8 atoms in a corners of the cube. Therefore 8 into 1 by 8, that is equal to 1. Now in phase centered, each phase at the center we have the atom. These phases are contributed to the 2 unit cells. Therefore, since there are 6 phases are there, 6 into 1 by 2 will be equal to the 3. Therefore, the total number of atoms in phase centered cubic lattice is 3 plus 1, that's equal to 4. So, once again, in simple cubic lattice, only one particle is present in the unit cell. In body centered cubic lattice, 2 particles are there. In phase centered cubic lattice, we have 4 particles in the unit cell. In hexagonal close packed structures, so here also we have given. So there are totally the 12 atoms. So the 12 into 1 by 6. So it will be the 2 atoms at the axis. The next, the 2 atoms are there in the phases. 2 into 1 by 2 will be 1 atom in each phase. And the 3 atoms are there in the hexagonal cube itself. So therefore it is the 3 plus 2 plus 1. So totally the 6 atoms are there in the hexagonal close packed structure. This is how the number of particles per unit cell is calculated. Lastly, we take another property of this, that is called the radius ratio. The ratio of the radii of the positive ion and the negative ion is called the radius ratio. Mathematically, it is given as radius ratio is equal to radius of the positive ion or the cation divided by radius of the negative ion or the anion. The effect of radius ratio in determining the coordination number and shape of the ionic crystals is known as radius ratio effect. The radius ratio can be used in determining the most stable form of arrangement of ions in the crystal lattice of an ionic solid. Here I have given the radius ratio, and based upon the radius ratio, what would be the coordination number and what type of the void is, and the examples of these categories. If the radius ratio is less than 0.155, then the coordination number will be 2 and the compounds are linear, the crystal. If the radius ratio is between 0.155 to 0.225, then the coordination number will be 3. It is having triangular planar, and the example is boron trioxide. If the radius ratio is between 0.225 to 0.414, then the coordination number becomes 4. It is having tetrahedral void, and the example zinc sulfide and cuprous chloride. So if the radius ratio is between 0.414 to 0.732, then the coordination number is 6. It is having octahedral void, and examples are sodium chloride, magnesium oxide. Similarly, if the radius ratio is in between 0.732 to 1, then the coordination number will be 8 and the void will be cubic. Examples are cesium chloride, ammonium bromide. If the radius ratio is 1, then the coordination number will be 12. They have close packing, CCP and HCP close packing, and those are nothing but they are the metals. This is how, knowing the radius ratio, we can judge what type of that the compound is. So students, go through the whatever I have said so far about the ionic solids and the read 2 to 3 times to understand these aspects. Thank you.